Okay, let's proceed to subtopic 39.5, the wave properties of particles. So, based on the concept of dual symmetry, if there is a wave, there must be a particle as well, right? One of the scientists that come up with this idea is Louis de Broglie. He postulated that because photons have both wave and particle characteristic, perhaps all forms of matter have both properties as well. This highly revolutionary idea had no experimental confirmation at that time. Okay, according to de Broglie, electrons, just like light, have a dual particle wave nature. So how does it come out? Right, based on E is equivalent to mc squared. This is from Einstein concept. Energy is equivalent to mass of the object, okay, times with the speed of it, c square for, or c square here, since the speed of light is the speed of EM wave or c. So from here, m times c dot c, where m times c is actually momentum. So from this, okay, we can rearrange to have interest in terms of a momentum is equivalent to energy over the speed of EM wave. Right, and we know that energy is equivalent to HF. Right, based on C is equivalent to lambda F. From here, we can have P is equivalent to H over lambda. Right, or we may rearrange it according to this. If we are interested in the lambda, is equivalent to H over P, where H is the Planck constant and P is the momentum. It could be mv, it could be mc, it could be mu. And from here, we know that all the time from Planck's hypothesis, E is equivalent to HF. So to know the frequency of a particle characteristic, we know that frequency is characteristic of wave. If a particle can have a behavior of a wave, it can have a frequency. So the frequency of a particle is equivalent to E over H. Again, H is Planck constant. So from this equation, we can see that any particle also can have the characteristic of the wave. So if you see here, this is a story about the particle. And if you see here, this is a story about a wave. When we combine this, it means that the particles or the wave can both have behavior as a wave or as a particle. We call it dual nature. Wave, we call it dual particle wave nature. Or in simple, certain books also put it as duality of wave particle. The problem of understanding the dual nature of matter and radiation is conceptually difficult because the two models seems to contradict each other. This problem, as it applies to light, was discussed earlier. The principle of complementarity states that. Okay, now let's move to electron diffraction. Okay, where in this process, the electron, the particles, going to have a diffraction process, where from here we are going to observe a wave behavior, where we have fringes happen. If it is behaving as a particle by right, whenever the electron passing through the slit, the double slit, okay, only two image going to be produced on the screen. However, it can be observed that we are going to have fringes. It means that diffraction happen, and finally constructive and destructive interference happen, proof on the screen. So it means that the electron, which is considered as particle only by classical physics, now can behave as wave. So this is the real image by the electron. This is very few electron used, okay, in number of 20 to 30 electron used. Here when you have a quite big number, okay, hundreds of electron is used. But now if you have more, okay, still we don't observe the pattern clearly. But when you have more than 1,000 of electrons used as the electron beam, okay, now you are going to observe clearly. Seems like here is bright fringe, dark fringe, bright fringe alternating. Okay, so this is a proof that particle, which is electron, can behave as a wave. Alright, so it brings us to principle of complementary. Okay, what is principle of complementary? It says that the wave and particle models of either matter or radiation complement each other. Okay, so it means that it exists, it coexists. It's just that based on duality of particle wave nature, we only can observe one characteristic at one instant. Okay, we cannot observe both behavior or characteristic at the same instant. Right. So wave particle duality in double slit experiment, this is actually similar to the previous diagram. If you have particles, okay, by right, you're going to have only two image on the screen. But by using electron, the number of the electron is increased very large in amount. Then finally you're going to have fringes like this, which is the pattern can be said similar to the pattern observed when we use wave as our source. So the Broglie states that matter can have wave-like properties. So means that electron, baseball, even ourselves actually have the characteristic or properties of wave-like. Right. So this is the Broglie wavelength is equivalent to Planck constant over the momentum. So here we can see here, if we're talking about accelerated electron, the mass of it, this amount, the speed is very big, and the lambda of it is 120 picometer. Okay, Fullerence, okay, cobalt 60, the mass, the speed, and the lambda. However, for golf ball, okay, the mass quite bigger, okay, much bigger compared to these other two particles. The speed slow, very slow, and then in comparison to the other two particles, and then the lambda is much smaller. When you have lambda is very small, you cannot observe interference pattern by the golf ball. Why is it? Because there is no separation distance or slits can be used to observe the interference pattern of fringes, because the lambda must be bigger than or equals to the separation distance. If we see here, the lambda for the golf ball is 4.9 times 10 to the power of negative 22. So means that it's very small, and we don't have any material that is less than, okay, this amount, because the size of separation distance between atoms, one atom to another atom, the separation distance between center to center is about 1 times 10 to the power of negative 10 meter. So in comparison to this, we cannot have any material which is smaller than this. Right, example 39.5, wavelength for microscopic and macroscopic object. Microscopic means it's tiny, miny things. Macro means it's bigger. Okay. A, calculate the Broglie wavelength for an electron. Given mass to this. By the way, the mass of the electron can be used or provided in the list of constant from your calculator. Moving at 1 times 10 to the power of 7 meter per second. So the lambda based on wavelength of the de Broglie is equivalent to Planck constant over the mass times with the speed. So you have this kind of lambda, 7.27 times 10 to the power of negative 11 meters, which is bigger compared to the size of an atom. So it's possible to have interference, diffraction, and finally constructive destructive interference that results in fringes that we can observe on the screen. Then B, a rock of mass 50 gram is thrown with a speed of 40 meter per second. What is its Broglie wavelength? So the Broglie wavelength is equivalent to h over momentum. So means that the object, the particle, only going to have the Broglie wavelength whenever it has velocity. Okay, whenever it is in motion. So if you substitute everything here, then you will get 3.3 times 10 to the power of negative 34 meter, which is there is no object which is equals to or smaller than this size to be the slit, right? So one of the application is the electron microscope. In electron microscope, okay, we are going to observe, okay, a sample, place, okay, a flat on the flat holder here, specimen holder here, right, where we are going to use electron gun that going to be moved and focused by using cathode, anode, electromagnetic lens, okay, the coil, the electromagnetic condenser lens, and so on, so that we're going to project the electron onto the specimen, right? And finally, we are going to observe, okay, the image of our specimen. It's more powerful compared to the normal or regular microscope, because the electron microscope has much greater resolving power, because it can accelerate electrons to very high kinetic energies, giving them very short wavelengths. No microscope can resolve details that are significantly smaller than the wavelength of the wave used to illuminate the object. The shorter wavelength of electron give an electron microscope a resolution that 1000 times better than that from the visible light used in optical microscope, or we call it normal microscope. As a result, an electron microscope with ideal lenses would be able to distinguish details approximately 1000 times smaller than those distinguished by an optical microscope or our common microscope. Right, that is why the electron microscope is way better. It can produce this kind of image, right? This is actually a photograph by using a scanning electron microscope shows significant details of cheese mites. Okay, this mite is so small, with a maximum length of 0.7 mm that ordinary microscope cannot reveal the miniature anatomical details like this: how many legs, how many hairs. Alright, so last one, the double slit experiment revised. So we have now going to repeat the same experiment for a young double slit experiment, but instead of using with light beam, we are going to use electrons here to prove that, okay, again, that particle can behave as a wave. Right, so similar arrangement. We have the distance from the slit to the screen much bigger compared to the size of the slit, the separation distance, the d, and then this is a central axis. Okay, so path different. This is path taken, okay, by the slit number 1. This is a path taken by the slit number 2 to arrive at this point. And again, we have this angle is similar to this angle, and the path different between, okay, slit 1 and slit 2 is symbolized as delta. The delta is equivalent to d sine theta. For bright fringe or constructive interference, that path difference, d sine theta, must equivalent to m lambda, where the m is the integer. So what are we going to observe? If you use only 28 electrons, okay, no regular pattern appears. Just seems like a normal image of particles. After 1000 electrons, a pattern of fringes begins to appear. Okay, then if you use 10,000 of electrons, the pattern looks very much like the many electron result in D. Okay, so two slit electron pattern for many electron results, more than 10,000. So it's clearer. So means that it proves to us that particle, which is electron, can behave as a wave. That's all for this topic. Thank you very much for watching. Do not hesitate to ask any question regarding this lecture.